Thermodynamics example 14. In this example, we've got two particles, P and Q, and their masses are 2m and 3m. So sometimes we have an algebraic mass rather than just a numerical mass. So 2m and 3m, this is particle P and this is particle Q. They're attached to the ends of a light, inextensible string. So remember what that means. Lightness means the tension is constant all the way through the string. And when it's inextensible, it means that both masses will have the same acceleration. So when we let go of this system, presumably the larger weight will go downwards and the lighter weight will go upwards. We also have what we say at the top, which is a smooth fixed pulley. This pulley at the top is smooth. What that means is that it doesn't create any tension. And so the tension on one side will be the same as the tension on the other side in this string. So that's the answer to part B. Make sure you learn those modelling assumptions from chapter 1. Now we just put some forces on our diagram. We've got a weight of 2m times g and 3m times g, and then we've got some tensions. I'll call that T1 and I'll call that T2. Now, because this is a smooth pulley and because we have a light string, what that actually means is that T1 and T2 are equal to each other. So I'll just call them T when I do my calculations. It says that the system is going to be released from rest. So I'm going to make the assumption the heavier mass will go downwards. I think that's a reasonable assumption. And the lighter mass will go upwards. So the way to tackle a situation like this, where you've got motion in one direction and motion in the other, is to treat them separately. So if I do F equals ma for Q, I'm going to do it in the direction of motion. So I'm going to do it downwards. I'll have 3mg minus the tension, I'll just call it T, equals 3m, the mass, times A, which we don't know. If I do the same thing for P, but upwards, because that's the direction of motion, T pulls up, 2mg pulls down, and it's mass times acceleration. Now, I've done it like that on purpose to form a pair of simultaneous equations, and you'll notice that one of the t's is negative and one is positive. That's because one of the t's is resisting motion, like on this 3m, and one of the t's is pulling the object forward. So we've got one negative and one positive. Now, the reason why this is quite nice algebraically is because if you add those two together, the t's cancel. T is not what we're trying to find in part A, we're trying to find A, the acceleration. So these two t's will cancel. You'll have a minus t and a plus t, which cancel out. So adding together this left-hand side will leave me with 3mg minus 2mg, which leaves you just with mg on the left-hand side. And that would always happen when you've got one going up and one going down. On the right-hand side, we've got 5ma when we add them together. So if we cancel out the m's, we'll get g equals 5a, and so the acceleration is g over 5. Part B we've already talked about, the modelling assumptions. Now to find part C, the tension, all you need to do is substitute back into either one of these two equations and see what you get for tension. I'm going to substitute it into the second one because T is positive there. So T minus 2mg will equal 2m multiplied by A, which is g over 5. Bring the 2m over. That means that T is 2mg plus 2mg over 5. What I would do here is count in fifths. So 2 whole ones is 10 fifths. We've got another 2 fifths here, so that's 12 fifths. So it's 12 fifths of mg. So that's the tension, that's the force, so it's measured in newtons. We've now got to find the force exerted on the pulley by the string. Now, if you think about this pulley at the top, it's got a string going over it and pulling down on both sides. And we know that that tension is the same throughout the string. So we've got a tension pulling down on both sides, and we know that it's equal to 12 mg over 5 on each side. So 12 mg over 5, and you've got it pulling down twice, once on each half of the string. And so the overall force pulling down on that pulley is 24 mg newtons. Moving on to the final part of the question, we've got to find the distance moved by Q in the first 4 seconds, assuming P doesn't reach the pulley. Obviously, if P reached the pulley, it would bang into it and stop, and then the motion would be different. But we're just going to assume that it doesn't reach that pulley. So T equals 4. We know the acceleration is g over 5. And I think the system was released from rest, if you remember the question. So U is 0. And we have to work out the distance that this particle Q has gone. Now, remember, the distance moved by P and the distance moved by Q will be the same. So it doesn't matter whether you're imagining P or imagining Q. It will be the same distance on either side. So we know that S equals UT plus a half AT squared. So U is 0, so the first part will be 0. And then we have a half times A, the acceleration of the system, times T squared, 4 squared, 16. Put that in your calculator, and it works out to be 15.6 something, about 68. And so when you round it off, because we're using G as 9.8, we should really round to 2SF. And so to 2SF, it's gone 16 metres.